Hello, everyone. This is Professor Ma, and this is the section on limits, the second part. Okay, this one is more about computations. And from the last sections, we have the following fact. If a function is an elementary formulas, and if I can plug in a number a into the formula, it's well defined, no problem. Then the limit as x approach a, it's the just plug in the function values. Okay, and so for example, let's see if for instance, if I have a polynomial and if x approach a, then you just plug in the numbers. So for example, x approach 2, okay, x cubed. And meaning that when x become closer and closer to the number 2, and you keep computing the cube, then the answer is going to get closer and closer to 8. And that is true for all the elementary functions: sine, cosine, log, exponentials, square roots, etc., etc. And if I make a quotient of two polynomials, as long as the denominator is not 0, if I want to find the limit, I can just plug in the top and plug in the bottom, find out where the numerator and the denominators goes. So if x goes to 0, then I put 0, and then x 0, 0, so I got 2 over minus 3. The limit, the quotient you on the calculator, you become closer and closer to minus 0.6666, the minus 2/3, the expansions. Okay, and of course this is these formulas. Then of course this process breaks down when x approach the numbers x approach a boundary number, which we cannot plug in. These are known for the ones we can plug in. So what I mean we cannot plug in? Well, then it gets a little bit more complicated. So one place that we very often have to decide the limit is when we form, say, fractions. And the formula is a form of fractions. And I don't just mean polynomial over polynomial, maybe trig functions over polynomials, or maybe log function over exponential function, etc., etc. Some sort of fractions. Okay, so let's take a look at the limits of our fractions. So I have two functions, f of x and g of x. Okay. And I form the fractions f over g. And if they both have limits, and then as x approaches a, little a, and then the fraction then will just approach whatever the limit of the numerator divided by the limit of the denominator. This is quite clear. The last example we had, right? Now, however, if the second case is what happened now if one of them behave wildly, blows up, do something, it can go to infinity. Okay, let's look at the first case. Let's suppose the top part, A, is bounded. That is, it stays within certain numbers, let's say from 10 to minus 10. Okay, just keep going back and forth between this boundary. But the denominator, g of x, downstairs, become bigger and bigger, goes to infinity. Then the fraction they form is very small. Doesn't matter what sign, positive small number or negative small number, they go to 0. So the limit will go to 0. If I reverse these, I keep the bottom, okay, for example, here's an example. Okay, the bottom become bigger and bigger, and the top stays between 1 minus 1. So as a whole, the fraction is very small. So the limit is 0. Flip it around, the fractions around, say what happens if the bottom stays between minus, bounded, but the top becomes bigger and bigger. Well, these ones, if we look at the absolute value of the fraction, so if I can guarantee the fraction is always positive, then no doubt, because the denominators stays, but the numerator becomes huge, then the fraction becomes very large. then the limit goes to positive infinity. But if I remove the absolute value, then I have the problems of the output, the fraction can be very large positively or very large, quote unquote, negative. It can bounce back and forth. So the fraction behaves very chaotic. Okay. So for example, here is say example where everything's positive, but the numerator becomes bigger and bigger. The x goes to infinity, but the bottom is always between -1 and 1. So the denominator, so the whole fraction goes to infinity. But if I remove the absolute value, then I really cannot tell the behavior of each fraction because it depends on what x is. X becomes big. Sin x might be positive or negative. Therefore, the fraction might be very large positive or very large negative. And so this is a chaotic back and forth. If I try to plug in, I look at my computer or my calculator, punching number x become bigger and bigger, but the output becomes, I cannot recognize a pattern. So we will say this is truly undefined or chaotic, undefined and chaotic. Okay. So again, this chaotic is different from the fact that something like limit x approaches 0, 1 over x squared, this is undefined, but I know the behavior, this goes to infinity. And this is not chaotic. This, I know the quotient steadily goes up, become bigger and bigger and bigger. The behavior I know for this one. But this time, I don't know the behavior because it's oscillating. Now, so we just went through the form that the type of conclusive form. There's these three forms I can make definite conclusions. And here are the forms of quotients which I cannot make conclusions. So-called 0 over 0 and the infinity over infinity, fraction forms. It says, suppose the fraction, the top goes to 0 and the bottom goes to 0 as the number approach x are plugging closer and closer to a, or the top goes to infinity, the bottom goes to infinity. We call these type of inconclusive. What mean inconclusive? It means plugging zeros, get 0, 0, infinity, infinity is a dead, it's on that dead end. It tells us nothing. And tells us we have to find some other way to do this problem. Like what? One of the typical ways is make it clean up the four fractions, simplify. Like for instance, this. If I try to plug in 0, I get 0 over 0. It's an inconclusive form, but right? If I plug in 0 on top, 0 on bottom, I get 0 over 0. I said, oh, gee. Let me do something else. What? Let me cancel the x because algebra cleanup, I get 1. So because the fractions x over x is always 1, except at 0. So in other words, the limit as x becomes closer and closer to 0, the limit will be 1. And what's the difference between the function x over x and the function, constant function 1? But there's difference at one location, at one point where with x equal to 0. For the constant function, it's one complete line. For the function x over x, it's the same line except you have a hole at x equals 0 because it's undefined. Okay. And we're saying as limit as x comes closer and closer to 0, where does the blue dots go to? Goes to 1, so the limit is 1. Okay. So again, these are 0 over 0 form. Why? Because when we try to plug in a number, I will get a fraction 0 divided by 0. Stop. Go back to the formula, change it, clean it up, cancel some things. For top one, cancel x minus 1. Okay, so this 0 with 0, no good. So and cancel, reduce, it gets then plugging again. Okay, now it makes sense. So no one have. Okay, we have that. Okay, and the bottom one, right? Same thing. If I try to plug in 0, I get 0. Well, if h becomes 0, okay, so this h go to 0. If h go to 0, then I got root 2 minus root 2. Root 2 minus root 2 is 0. So I got 0 for 0. So this is the 0. So what? So I need to do something else. Like what? Change it. What's a square root problem? So probably use conjugates. Okay. There's only one basic trick in this type of format. Multiply by the conjugates. What does that do? That changed the form of the limit, plugging 0 in here versus plugging zeros in here. Okay, because they're the same. But this one, I know what it is, because when h becomes 0, basically I got minus root 2, got 2 of those. So minus 2 root 2. Okay. So those are the steps that we use to look at 0 over 0 and the forms. Usually change the formula, fractional formula. Now, how about the other inconclusive infinity over infinity? Okay, if it's infinity over infinity, got your fraction, the top becomes infinity, the bottom becomes infinity. There must be parts of the top going to infinity, parts of the bottom goes to infinity, the biggest. So you should locate which part of the formula is going to the infinity the fastest. You say, well, later on we'll have a more precise idea of who goes to infinity, which formula goes to the infinity the fastest. Okay. Like for instance, here's a problem that goes to, if I try to plug in infinity, and I say when x goes to infinity, and the 3 times x becomes bigger and bigger, it goes to infinity. 2x squared, that goes to infinity. So basically, I'm saying this is telling you, if you're going to plug in very large numbers, what's on your calculator, you're going to look at a very large number divided by a very large number, which is a qualitative statement. Okay, it means nothing in quantitative. It doesn't tell you. You just say, oh, it's a large number, large number. So what you need to do is you need to change it. How? Well, which part goes to infinity fastest? X squared. Okay, think about it, because whatever x is, you have a square for a large number. Once you square, it's a lot bigger. So divide everybody by x squared. Okay. Then you got individual terms like that. Now look at the individual component. X goes to infinity. Now this goes to 0 because that fraction denominator goes to infinity. And same thing with that part goes to 0. And so what's left is telling you eventually the numerator will be a very small number, 0, and the bottom is 2 minus 0, or 2, basically it's 2. Okay, so the limit 0. Here are 2 other possible scenarios as x goes to infinity. Okay, and the second for part B, that goes to infinity, both top and bottom, and which part goes to infinity the fastest? Well, the x squared going at the same speed, top and bottom. So divide everything by x squared. We change the look of the fractions into these. Now, when x goes to infinity, then the part that goes to 0 is that part. And so then the answer collapses to 3 over 2. So that's a limit. Notice when the degree are the same, then they cancel out. And then you just get a number 3 divided by 2. Now, the third case is the top has degree bigger, then you probably expected that then the limit will go to infinity because the top goes to, you have to cube it, it goes a lot faster than square. Okay, it shows. Okay. So these are type of example we have for when x goes to positive infinity. Okay. In particular for rational formulas, okay, and so for limits of rational formula, one more time, the lower degree term doesn't matter. So when x goes to infinity, okay, we're talking about a boundary when x becomes very large in your graph, that's way out to the right, way out to the left. Okay, the graph is going to look like eliminates the lower degree terms, clean up the fractions. Basically, it looks like this monomial. Okay, and we'll have 3 examples like with the one we did. Then you can possibly then the limit 0. The limit is the coefficient. You have this if they have the same degree. Same degree top and bottom, then it goes to the coefficient 3/2. If the top has higher degree, then the thing blows up to infinity. Okay, so these are the basic 3 cases. Okay, so in other words, so for rational forming, we can just drop the bottoms, the lower degree terms, and just take the head, the biggest degree, and then clean that up and then see what happens. Then, oh, there's a constant pi over e because x fourth over x fourth cancels. For algebra, for algebraic formula, same thing. And look at the highest degree term. Oh, that's a 4.3 up there. Okay, all right. So you have to look at it. And the bottom, the highest degree is 4.2. And cancel the degree. You still got x to the 0.1 left. But that still makes it infinity, right? So it's going to go to the limit's going to minus infinity. Okay. Because you still got the x, the root of x, but the 10th root, but that's enough because x is going to infinity. So the 10th is going to infinity. Okay. So these are the behavior in rational functions. Now, one of the most important limit that cross family from algebraic family into the trig family is a limit as x go to 0 comparison x versus sine of x. If I plot this, if I plot these 2 graphs on a calculator, okay, notice between minus 0.8 to 0.8, I think these are in radians. I mean, in the middle over here, that's the indistinguishable. In other words, for x is very small, okay, for small x's, that means x close to 0. Then the value of sine x is roughly equal to x. Okay. And so for example, sine of 0.5 degree, okay, yeah, again, oh, by the way, this axis has been in radian measurement. So if I'm talking about 0.5 degree, you have to convert that into its radian. Okay, that's going to be pi over 360. So that's approximately that. If you type it in your calculator, that's what it is. Here's a proof. We're going to use the following fact, which we call sandwich theorems. Okay, and suppose I know the limits of h coming from this side and coming from that side. I know the limit coming at one locations, and I want to know what the limit for the g is. Then, well, because g is being sandwiched between, funneled into that point, so the limit of g has to be the same location. Okay, so that we call the sandwich principle, or squeeze principle, if you like. And here's a proof for the limit as theta go to 0, theta divided by sine theta is equal to. Okay, and it's a geometry proof. Okay, theta is this arc, and the sine of theta is the height, the blue line. Okay, now when theta go to z, by the way, tangent theta is the outside over the height over there. Okay, and on the pictures we can definitely tell tangent theta bigger than theta, then bigger than sine theta. Okay, now we're going to divide everything by sine theta. Then we have 1 less than theta divided by sine theta less than tangent divided by sine theta is 1 over cosine theta. Okay, now at theta go to 0, okay, cosine on the right hand side goes to 1. So this side is going to 1. Okay. And that's it. So where does theta go? Sine theta is limit sine theta goes to 1. So sine theta is roughly equal to theta for very small theta. In other words, what we meant by that is if I'm in a very small angle, I have a very small angle, okay, and then basically the blue height and this arc line theta, this little portion, basically these are the same length. Smaller the theta is, the more they are equal to each other. So that's what this theorem says. Okay, and also this theorem says as long as f of x goes to 0, okay, when x goes to some number, okay, and you have a formula x plus x goes to a, some number a, then f of x goes to 0, okay. Then since this is going to 0, sine of x, f of x will be equal to the argument, whatever f of x is. Okay. So, for example, when x goes to 2, okay, x minus 2 go to 0. So sine of x minus 2, this is roughly x minus 2. Okay, sine of x minus 2, roughly x minus 2 is x minus 2 divided by x minus 2 is equal to 1. Okay, or this one, it's a different way of looking at the way. So sine of x, when x goes to 0, twice of x goes to 0, right? So sine of 2x is roughly what? Twice of x. And what's x divided by 2x? Well, x cancels out, x is 1/2. Okay. Again, if you have a sine of a small number is roughly equal to that small number. Okay. And here's another way of doing it. You know, a sine of 2x and over 2x, and the sine of 2x over sine 2x is 1. But this is theta. This is theta. The sine of theta over theta is 1. So this part is 1. And so the answer is left with 1/2. Okay. For this one, we multiply by the conjugates, and again use the conjugate trick, and then we obtain the sine x over x squared over x squared, and that of course sine x squared, and that sine x over x as x becomes 0, that goes to 1. Square of 1 is 1. When this part, when x is 0, cosine 0 is 1. So on the right hand side, that's 1/2. So the whole thing collapses to 1/2. Okay, and that's it. That's a basic tricks in doing limits. Okay, that's it. Bye bye.